Now that we've done that review, let's go on with the second half of this tutorial and finish off this practice problem starting with part A. We're no longer dealing with a single gene. As you recall, we're dealing with two genes, one for coat color and one for hair length. And we've been given some numbers of progeny resulting from the guinea pig parents being bred together. The question asks, what must be the parents' genotypes? The fast way to answer that question is to recognize that the progeny numbers from part A resemble an example you saw in lecture of what happens in a dihybrid cross. With a dihybrid cross, two F1 generation pea plants that were heterozygous for two genes and that had both dominant phenotypes for those genes were bred together. By doing the full 4x4 Punnett square for the two gene cross, we can see that their resulting pea plant progeny in the next generation, the F2 generation, would have had a 9:3 to 3:1 phenotypic ratio. In other words, 9/16 of them would be yellow and round, 3/16 would be yellow and wrinkled, 3/16 would be green and round, and 1/16 would be green and wrinkled. This 9:3 to 3:1 ratio in phenotypes corresponds pretty much exactly with the guinea pig progeny numbers that we have here in part A. What does that mean for the parents? It means that, as in the example with the pea plants, if the progeny had this characteristic 9:3 to 3:1 ratio, then the parents must be double heterozygotes for both genes, and you must have an example of a dihybrid cross. For our guinea pigs in this practice problem part A, that means that they both must be big C little s little s heterozygotes. This 9:3 to 3:1 ratio coming out of a dihybrid cross is another key ratio to remember and try to recognize. But what should you do if you don't remember this ratio, or if the progeny numbers in a problem don't correspond as obviously with the 3:1 or 9:3 to 3:1 ratios you're so familiar with? There are different ways to approach and work through these problems. For this tutorial, I took a simple approach towards identifying genotypes when given phenotypes and numbers of progeny, as you are given in this problem. First, we'll list everything we can figure out about the parents' genotypes from their phenotypes. Then, we'll look at one independently assorting gene at a time. First, the coat color gene, then the hair length gene, and use these progeny phenotype ratios and what we just reviewed about 2x2 Punnett squares and possible progeny phenotype ratios to figure out the rest of the parents' genotypes. I'll show you what I mean. Here, let's start with part A and go through it again in this fashion. Begin with the parents' phenotypes. What do they tell us about their genotypes? Both parents in part A have dark coat color. Dark coat is the dominant phenotype. That means for their coat color gene, both parents can have either big C, or big C, little c as their genotype. We can't narrow it down any more than that just from looking at their phenotype. The same thing is true for their hair length phenotype. Both parents have short hair, so both parent guinea pigs could have either the homozygous dominant genotype, big S, or could be heterozygous, big S, little s. We can't tell which for either gene until we analyze the progeny that resulted from the cross. One thing we can do with this practice problem with two independently assorting genes is to look at results for one gene at a time, separately from the other gene. This can help simplify things for us, since we only have to remember and think about the simpler results of the 2x2 Punnett squares that we reviewed at the beginning of this tutorial. Let me show you what I mean by starting with the coat color gene. Let's ask first, how many guinea pig progeny have the dominant coat color phenotype with dark fur coats? We can add those numbers up and see that the answer is 89 plus 31, or 120. Then, how many guinea pig progeny have the recessive phenotype of an albino coat color? Add up the progeny numbers and you can see that this is 29 plus 11, or 40. If we compare those numbers, we can see that there are 120 dark coat dominant phenotype progeny to 40 albino coat recessive phenotype progeny for a 3:1 phenotypic ratio. Now, let's ask ourselves, where have we seen that ratio before? We learned about it back with our 2x2 Punnett square, where both parents are heterozygous for the gene in question. When both parents are heterozygous, then 3 out of 4 of their progeny, on average, will have the dominant phenotype, and 1 out of 4 will have the recessive phenotype. The result of this is that when you look at progeny numbers, you can see this 3-to-1 phenotypic ratio in the progeny from a heterozygote to heterozygote cross. Because this is exactly what we see here from the progeny numbers looking at the coat color, we know that for the coat color gene, the parents must both be big C, little c heterozygotes. Now, do the exact same thing for the other gene, the hair length gene. Remember to look at just the hair length phenotypes separately. First, ask yourself, how many progeny have the dominant phenotype of short hair length? The answer is 89 plus 29, or 118. How many progeny have the recessive phenotype of long hair? The answer is 31 plus 11, or 42 guinea pigs. Compare 118 to 42, and you see that, again, this is nearly exactly a 3-to-1 phenotypic ratio, suggestive of a heterozygote to heterozygote cross for the hair length gene. Thus, we can identify the parents as both being big S, little s heterozygotes for the hair length gene. And now we have their genotypes and part A is finished. I'll walk through parts B through parts G in exactly the same way to give us more of a sense for this way of thinking. However, I'd urge you, if you're following along, to actually stop and pause the tutorial before each part and attempt to work through each sub-question on your own on a piece of scrap paper in advance. Then come back in and check your work in the tutorial. Alternately, another good approach would be to listen all the way through, then go back on your own with a few pieces of scratch paper and pencil and work through these problems on your own by hand. Speed and accuracy in answering these sorts of problems is really improved by practice and repetition on your own, which you won't get just by watching the tutorial video. With that said, on to part B. Begin again by figuring out everything you can about the parents' genotypes, that is, the answer of the problem that you want, by looking at their phenotypes and seeing what information that gives you. Both parents in part B have the dominant dark coat phenotype, so both could be either big C homozygotes or big C heterozygotes. One parent has the dominant short hair length phenotype, so they could be big S, or big S, little s. The other parent actually has the recessive long hair phenotype, though. So they only could be homozygous little s for the hair length gene. Now again, let's look at the progeny numbers, focusing on one gene at a time. How about coat color? How many baby guinea pigs from these parents had the dominant dark coat color? 18 plus 19, or 37 total. How many had the recessive albino coat color? 0. None of them did. That means that 100% of the progeny have the dominant coat color phenotype. Now again, think back to the introduction and the handful of possible outcomes for 2x2 Punnett squares. Where have we seen a situation where all the progeny have the dominant phenotype? Well, we saw that it happens whenever one of the parents is homozygous for the dominant allele. That means for both copies of the gene, they have the capital letter dominant allele. So in a simple 2-allele dominant recessive setup, like in this practice problem, any offspring they generate will have to have inherited a dominant allele from them, and therefore will have the dominant phenotype. Notably, this will be true regardless of what the other parent's genotype is. So we can go back to part B and say that because we saw this phenotype ratio in the progeny, one of the parents has to be homozygous dominant, big C, for the coat color gene. The other one could be big C too, or it could be big C, little c. We can't tell from just this given information. Okay, now what about the other gene, hair length? How many of the progeny have the dominant short hair phenotype? 18 plus 0 is 18. How many have the recessive long hair phenotype? 19 plus 0 is 19. Here, we're seeing a 1-to-1 phenotypic ratio. Not only that, but we already know the hair length S gene genotype for one of the parents. One parent is homozygous recessive. In keeping with our theme, we should think at this point, where did I see that before with my review of 2x2 Punnett squares? We saw it with the test cross example. With the test cross, one parent is homozygous recessive. If the other parent is heterozygous, then half the progeny will be heterozygous and have the dominant phenotype, and the other half of the progeny will be homozygous recessive and have the recessive phenotype. Because of this, you get a 1-to-1 phenotypic ratio among the progeny. This is exactly what we see for hair length in part B, So we know that the other parent has to be a big S, little s heterozygote. And then we're done. This is as far as we can figure out the parent's genotype in this part of the problem. Next is part C, which you may be able to see looks very similar to part B and how it's going to go. Start again first by looking at the parent's phenotypes and gleaning all you can. The first parent has the dominant phenotype for both genes, short hair and dark coat color. So we know that they could be either big C, little c, or big C, big C. And they could be big S, little s, or big S, big S. The other parent has short hair, the dominant phenotype. So again, they could be big S, or big S, little s for their hair length gene. They have albino coat color though, so that means they have to be little c for the coat color gene, homozygous recessive. Then I'll look at the progeny for one gene at a time. Start with coat color. How many baby guinea pigs have the dominant dark coat color? 20. How many have the recessive albino phenotype? 21. This is that 1-to-1 phenotypic ratio again. And again, one of our parents is a homozygous little c recessive. What do we have again then? We've got the test cross scenario again, where one parent is heterozygous. So that means for part C here that the other parent has to be big C, little c heterozygous for the coat color gene. Now onto the hair length gene. How many progeny have the dominant short hair length phenotype? 20 plus 21, or 41 total. How many have the recessive long hair? 0. This means 100% of the progeny have the dominant phenotype. We just saw in part B what that must mean for the hair length gene for those parents. It means that one parent must be homozygous dominant, or big S, big S. The other parent could be either big S, or big S, little s. We can't tell which, just that it's not little s, since that parent is not long-haired. And those are the final genotypes for part C. Next up is part D. We'll work through it in the same way, starting with looking at the parents' phenotypes and ascribing what we can to their genotypes. For part D, we can see that both parents have an albino coat color. That's the recessive phenotype, so we know that they both have to be homozygous recessive, little c, for their coat color genotype. Both parents have the dominant short hair phenotype for hair length, so they could be either big S, little s, or big S, big S. Okay, now that we have that, we can see that part D is pretty nice in the sense that both parents are already figured out for the coat color gene. Both are little c for sure, just from looking at their albino coat color. That should also mean that all their progeny will be albino, which we can see checks out in the numbers in the table. So we only need to worry about the hair length gene for part B. Add up the number of progeny with the dominant short hair phenotype, it's 28. Add up the recessive long progeny, it's 9. Look again at those numbers and we'll recognize our old friend, the 3-to-1 phenotypic ratio, characteristic of two heterozygotes being crossed together. From that, we know that in part D, for the hair length gene, both parents must be big S, little s heterozygotes. Next up in the order is part E. What do we know from the parents' phenotypes? The first parent has both dominant phenotypes, so it could be homozygous dominant or heterozygous for both genes. For parent 2, they have a dominant dark coat, so could be big C, little c, or homozygous big C. They have recessive long hair though, so that identifies them as little s for hair length. What are the progeny numbers for considering just coat color alone? 29 plus 31, or 60 total, have the dominant dark coat phenotype. Then 9 plus 11, or 20 total, have the recessive albino coat. 60 compared with 20, that's the 3-to-1 ratio we've seen before, which we know indicates that the parents must both be heterozygous for the coat color gene. So we can simplify their genotype for coat color to big C, little c for both parents. For hair length, 29 plus 9, or 38 total progeny, have dominant short hair. 31 plus 11, or 42 baby guinea pigs, have recessive long hair. Compare these progeny numbers and we see a 1-to-1 phenotypic ratio in a setting where one parent is a recessive little s homozygote. This is a test cross situation where one parent is homozygous recessive and the other has to be heterozygous. Thus we can tell that the first parent in part E has to be big S, little s heterozygous, and we're finished with part E.